Now it's time to talk about Dalton's law of partial pressures. So we've talked about gas laws individually with the ideal gas law, the combined gas law, the individual gas laws, like Boyle's law, Charles's law, Hamilton's law, Avogadro's law. But what I want to talk about now is if I have multiple gases in a system, what's happening? What if I have a system that has multiple gases, but the gases are not reacting with one another, so they're not making some new gas that's a molecule together? They're just individual gas molecules in one system, such as the air around us. The air around us has O2, nitrogen, argon, CO2, water vapor, other things depending on where you live in the world. So the air around us, though, it's not like those gas particles are reacting to form a new molecule, they're just all coexisting. Dalton's law of partial pressures deals with this concept and helps us figure out how to figure out the pressure of the total system based on the individual pressures overall. To do this, we need to also understand mole fraction, what fraction of the sample is actually the component we're looking at. And then we use Dalton's law of partial pressures to also involve collecting gases over water. And we'll discuss why we need that and what happens. So Dalton's law of partial pressure states the pressure of a mixture of gases is equal to the sum of the partial pressures of each of the gases present. The definition of partial pressure is the pressure that an individual gas in a mixture of gases would exert if it were by itself at the same temperature and the same volume. So what it's telling me is the pressure total of the system is equal to the individual partial pressures of the gases that make up that system. So for example, again, looking at air, generally speaking, air is a huge portion of nitrogen, a chunk of oxygen, smaller percent argon, smaller percent CO2, and then whatever else is in the air where you happen to live. The pressure of air itself is due to the partial pressures of each individual species. So the pressure of A, component A, is equal to the mole fraction of A times the pressure total. So mole fraction and partial pressure. If I was to look at the example here of nitrogen, well, what's mole fraction? A mole fraction is the number of moles of the component you're looking at divided by the total number of moles of the sample. Partial pressure, so partial pressure of A is calculated by finding that mole fraction times and multiplying it by the total pressure of the system. Example, the mole fraction of N2 in air is about 78% or 0.78. 78% of molecules in the air are nitrogen. Remember, nitrogen is diatomic, so it's N2. Therefore, the fraction of that would be 0.78. If the total pressure was equal to 1 atmosphere, partial pressure of nitrogen, 0.78, times the total pressure of the system, the partial pressure of nitrogen would be 0.78 atmosphere. So again, it's how much is just that piece contributing to the total pressure of the system. That means that, the other, if oxygen is, I can't tell from here, 20% maybe oxygen, that means that 0.2 atmospheres would come from oxygen, and so forth. Let's work an example, because that tends to help people see it a little bit better. We have a 10-liter container of a mixture of helium, neon, and argon gases. At 125 degrees Celsius, the mixture has a total pressure of 842 millimeters of mercury. So P total is 842 millimeters of mercury. Remember, when I say millimeters, I mean distance. That is a distance. It means it has pushed the mercury up the barometer to that specific distance or length. 842 millimeters of mercury. The partial pressure of helium is 451 millimeters of mercury. And the partial pressure of neon is 114 millimeters of mercury. What is the mole fraction of each gas in the mixture? Well, first, I've got three things here: helium, neon, and argon. I know the partial pressure of helium. I know the partial pressure of argon, but it doesn't tell me the partial pressure, I know helium, I know neon. I don't know the partial pressure of argon. But I can find that pretty quickly, right? Because I know that the pressure total is equal to the pressure of helium plus the pressure of neon plus the pressure of argon. So the pressure of argon must be equal to P total minus the pressure of helium minus the pressure of neon. 842 millimeters of mercury minus 451 millimeters of mercury minus 114 millimeters of mercury. Pressure of argon here. I actually calculate this out. I don't actually have to do this, but there's different ways you can do this problem. So some students are going to see it better this way. 451, 114, let's see, 277. Now I've got all the individual partial pressures if I want them. But I don't know if you guys remember this. Pressure of A is equal to mole fraction of A times P total. That means the pressure of helium is equal to the mole fraction of helium times the pressure total. The pressure of neon is equal to the mole fraction of neon times the pressure total. The pressure of argon is equal to the mole fraction, or to the total, partial pressure of argon. Partial pressure of argon is equal to the mole fraction of argon times the total pressure of the system. So I can rearrange this equation. X sub A is equal to P sub A over P total to solve for the individuals. Let's do helium first. Mole fraction of helium, 451 millimeters of mercury divided by 842 millimeters of mercury. There should not be units on here. This gives me 0.536. No units. My units have canceled out. My mole fraction of neon, 114 millimeters of mercury to 842 millimeters of mercury gives me 0.135. Again, no units. And because I did go ahead and calculate the partial pressure of argon, I can go ahead and do the same thing. Partial pressure of argon, 277 millimeters of mercury divided by 842 millimeters of mercury gives me a total pressure here of 0.329. Again, no units. Now I made the comment offhandedly that I didn't actually have to calculate the partial pressure of argon. I need it later, so it's helpful to have. But I didn't actually have to do it this way. And the reason I didn't is that I can understand that the total mole fractions, so I'm going to erase part of this stuff. This portion here, you're going to need that for the next thing. There's a couple different ways we can do it for the next part B, but if you don't have that, please write that down if you want to do it, so we can see both ways we do it, because I'm going to refer back to it. Oh, I don't want to keep those. I'm just going to shove these over here. The reason I didn't need that is I know that the mole fraction of each species, the mole fraction of helium plus the mole fraction of neon plus the mole fraction of argon has to equal 1, because the actual percent abundance of each one has to equal up to 100%. So each one individually has to add up to 1. So if I want to find the mole fraction of argon, I could take 1 minus the mole fraction of helium minus the mole fraction of neon, and I would get the same answer, 0.329. So you could have found this either direction. Either way, it doesn't matter. But mole fraction of helium, 0.536, mole fraction of neon, 0.135, mole fraction of argon, 0.329. Now let's ask me what mass of argon is present in the mixture. I'm going to use Dalton's law to determine the partial pressure of argon. I'm going to do this at the top of the screen. Looks like I don't have room turn at the bottom. So, coming up here, first thing I'm going to do, use Dalton's law to determine the partial pressure of argon. Now, I already did that, but if I hadn't done it, I could do that by the subtraction, as we had just done. Partial pressure of argon is equal to the total pressure of the system minus the partial pressure of helium minus partial pressure of neon, giving me that 277 milliliters of mercury. Or I could understand my mole fraction equation. It's right here. My partial pressure of argon is equal to the mole fraction of argon times the total pressure of the system. The mole fraction of argon is 0.329. The total pressure of my system, I forgot, is 842 millimeters of mercury. And so again, I get that 277 millimeters of mercury. So either way, you can do it. We did it before to get the partial pressure, so I didn't have to do it again. But if you hadn't done it that way, if you had done the 1 minus the mole fractions, you would have had to find the partial pressure of argon. Then what I'm going to do is use PV equals nRT to calculate the number of moles of argon and then convert to grams. So PV equals nRT, rearranged, and is equal to PV over RT. This is the partial pressure of argon. The volume of the system is the same because all the gases are mixed together. R is a constant, and the temperature is the same for all of them because they're all mixed together. Partial pressure of argon is 277 millimeters of mercury. I do have to convert that to atmosphere, but I'm going to do it in the equation. I know 1 atmosphere is 760 millimeters of mercury. Question tells me it's a 10-liter container. I know my gas constant, 0.08206 liter atmosphere to mole K. And the temperature is listed in the question as 125 degrees C. I need to go ahead and convert that to Kelvin. That would be 398 Kelvin. Make sure units are canceling. Kelvins have canceled. Let's see, atmospheres have canceled. Millimeters of mercuries have canceled. Liters have canceled. I've got moles in the denominator for denominator, which makes it my numerator. I get out 0.1116 moles. It's 1 extra sig fig there. Just underline my sig figs of argon. Now, I don't have any room, but I'm going to make room. So I need to now find the number of grams that actually correlates to. So I'm going to shrink that to my grams up here. Number of grams. Why grams? Because it's asking me for mass, and mass means grams. 1116, underline where my sig figs are. Moles of argon. I look up argon in the periodic table, and I see it has a molar mass, or atomic weight of 39.95 grams per mole. Which gives me 4.46 grams of argon. So this question, part A, got my mole fractions. Part B, I've got my mass of argon. Let's work another example. What is the partial pressure of oxygen in a mixture that contains 0.3 moles of O2, 0.7 moles of N2, and 0.25 moles of argon with a total pressure of 1.1 atmosphere? Well, I want partial pressure. So P of O2 is equal to X of O2 times P total. I need to find X of O2. Number of moles of O2 divided by the number of moles total. So O2 plus number of moles of N2 plus number of moles of argon. I have 0.30 moles of O2 and I have 0.70 moles of N2, 0.30 moles of O2, and 0.25 moles of argon. Overall, that gives me 0.24. Again, no units because in the denominator they're adding up. So 0.7 plus 0.3 plus 0.25 is 1.25 moles. Moles divided by moles gives me no units. 0.24 is my mole fraction. Now I plug it into my equation. Pressure of O2 is equal to 0.24. Basically, 24% of the sample is due to oxygen. The total pressure of the system is 1.1 atmosphere. So I get out 0.26 atmospheres just due to the oxygen. Most students don't have a hard time with partial pressures once they can remember how to calculate mole fraction. But that, again, mole fraction is just figuring out what percentage of the sample is actually due to that species. So Dalton's law can also help us though if we collect gas over water. When a gas is collected over water, it traps water vapor in the gas itself. Water vapor, what is water vapor? Water forms a vapor. A vapor is when the species that you're talking about, in this case water, goes into the gas phase at a temperature it normally wouldn't be in a gas phase. What I mean by that is water boils at 100 degrees. So we expect water to be in the gas phase at 100 degrees Celsius, but yet we have water vapor all around us when we haven't reached 100 degrees C. If you put out a container, put out a thing of water on the countertop, depending on the temperature in the room, it will take longer if it's colder, less time if it's hotter out, but the water will evaporate away. And that's because water is able to enter into the gas phase even when it hasn't reached its boiling point. Hence, it has a vapor pressure. And so when gas is collected over water, water gets trapped in there as well. There will be water vapor present along with the gas you produced. So what you do to correct for this is you have to subtract out the water vapor, which is the amount of water vapor there is dependent upon temperature. You subtract out the water vapor from the measured atmospheric pressure to find the partial pressure of your actual gas. So let's actually apply this so you can see what I'm talking about. I want to know, calculate the volume of gas that could be collected over water when 6.75 grams of aluminum reacts with excess hydrochloric acid solution at 0.985 atmosphere, 15 degrees C, assuming a 90% yield. Now, the one part this question is not telling you that you would have to have on any assessment. On homework, you don't have to have it. Homework, you have to recognize that when it says collected over water, you need water's vapor pressure. You need to look up the vapor pressure of water at that corresponding temperature. On an assessment, of course, I would have to give you that value. But on homework, I don't have to. So you have to recognize when it says collected over water, that means go look up the vapor pressure for the corresponding temperature. So the water vapor pressure at 15 degrees C is equal to 0.0168 atmospheres. We need that value. Now we can go ahead and start looking at the question. Okay, it tells me I have aluminum reacting with excess hydrochloric acid. So I have aluminum, which I know is a solid. Hydrochloric acid I know is HCl. These two are going to react, and this is a single replacement reaction. So think about it like cation-anion swap, yes, but the hydrogen here is my cation, so that's going to swap out with my aluminum, meaning I'm going to form H2 gas. Hydrogen is a diatomic, so it will be H2, and the aluminum will replace that hydrogen in the compound. Now, chloride is a -1 charge. Aluminum would have a +3 charge when it forms an ion, so I need to have 3 chlorides for every 1 aluminum. Now I need to balance my equation. I have one aluminum on each side. I have 1 hydrogen on one side, 2 hydrogens on the other. So if I put a 2 here, That does not balance my chlorides. Now I've got 2 chlorides and 3 chlorides, so I need to put a 2 here and a 6 here. Now my aluminums are unbalanced. I need to put a 2 here. Now my hydrogens are unbalanced. I need to put a 3 here. So lots of work later, 2, 6, 3, 2, we got our balanced equation. Now we've got a balanced equation. We know our vapor pressure. We almost have everything we need to do this, okay? So what I like to do is kind of make a list of what I know. I know that I'm going to be using PV equals nRT. How do I know that? Because I'm using volume of a gas here. So what is my pressure? My pressure tells me 0.985 atmospheres. But it says collected over water. I know when it says collected over water, I need to subtract out the water vapor pressure. So I'm going to subtract from this 0.0168 atmospheres. My actual pressure here, 0.968 atmosphere. It's not a huge difference, but it's enough of a difference that you're going to get the question wrong if you don't do it. Temperature, 15 degrees C. I know I need that in Kelvin. By sig figs, I'm going to keep to just to the ones place, no decimal places. So 288 K. And I'm trying to find volume, PV equals nRT. I need my number of moles. What am I calculating moles of? The volume of gas that could be collected. I'm trying to find the volume of H2. That's what I'm trying to find. The volume of H2 collected. So my number of moles of H2, well, I know that I am reacting, let's see, where is it? 6.75 grams of aluminum with excess HCl, which means that this is my limiting reactant. So 6.75 grams of aluminum, convert that to moles of aluminum. Use my balanced equation. I see that 3 moles of H2 are produced for every 2 moles of aluminum consumed. And I get 0.375 moles of H2 being produced. I've got my pressure, my temperature, my number of moles, and my gas constant is a constant. So, trying to solve for volume. I'm going to move these down slightly so I can move the screen up. Again, PV equals nRT. If I'm solving for volume, that's nRT over P. I just determined that I could theoretically make 0.375 moles of H2. My gas constant is 0.08206 liter atmosphere per mole K. My temperature is 288 K. And my pressure is 0.968 atmospheres. My volume calculated out here is 9.16 liters, but this is my theoretical yield. I have not yet accounted for the fact that it's at assuming 90% yield. I could have done that here as well, but I like to do it at the very end. Assuming 90% yield. What that means is I have to consider that. I know my actual yield is 9.16 liters times 0.900 for that 90% yield. 8.24 liters is my actual yield. So I'm going to get 8.24 liters out of this system of H2 gas if I react 6.75 grams of aluminum with excess hydrochloric acid under these conditions. If I got a 90% yield, that would be my results. Let's do another one. What mass of water vapor is produced from the gas phase reaction of O2 with H2 in a 2.5 liter container, 28 degrees C, if the partial pressures of O2 and H2 are 0.98 atmosphere for O2 and 1.24 atmosphere for hydrogen. So what I need to recognize here is I am given partial pressures for both. I am told 2.5 liter container, 28 degrees C. So I'm given volume and temperature, but I'm given partial pressures for each species, which means this is a limiting reactant example. 0.98 atmosphere. I just put those in the wrong spot. 1.24 atmosphere. 0.98 atmosphere. So I need to figure out what my limiting reactant is so I can actually answer the question. We're provided pressures. So again, we are provided pressures for both O2 and H2, which is both reactants. And they're in the same mixture, meaning I can find the number of moles. This is a limiting reactant problem. We have to be able to recognize that. So let's go ahead and calculate the number of moles of each species and then see which one's my limiting reactant. Number of moles of H2. Again, I'm using PV equals nRT to do this. So PV over RT equals N. My pressure of hydrogen is 1.24 atmosphere. My volume is 2.5 liters. Gas constant 0.08206 liter atmosphere to mole K. And my temperature, 28 degrees C, is the same as 301 Kelvin. This gives me 0.126 moles of H2. Do the same thing for O2. I have 0.98 atmospheres of O2 in a 2.5 liter container. Gas constant 0.08206 liter atmosphere to mole K. And 301 Kelvin. This would give me 0.0992 moles of O2. Again, I can't just say oxygen is smaller, so it's a limiting reactant. I have to compare the two because it's not a one-to-one reaction. And either way, you have to compare it if you want credit on a test. So I'm going to ask, do I have enough H2 to react all of my O2? Number of moles of H2 needed. If I'm reacting 0.0992 moles of O2, it takes 2 moles of H2 to react 1 mole of O2. And I didn't actually calculate that, so 1 second, 0.992 times 2 would give me 0.198 moles of H2 needed. So again, I know I'm writing all over the screen here, but what this means is I have 0.126 moles of H2. I need 0.198 moles of H2 to react all of my O2. I don't have enough. Therefore, my H2 is my limiting reactant, and my O2 is my access reactant. I'm now going to use my limiting reactant to answer the original question after I shrink a lot of this stuff so I have space. So again, I'm going to use the hydrogen I have, moles of hydrogen I have to answer the original question. What mass of water vapor, so number of grams of H2O, is dependent upon the number of moles of hydrogen I actually have? 0.126 moles of H2. 2 moles of H2O are produced for every 2 moles of H2 consumed. H2O is 18.02 grams per 1 mole. I see my final answer, 2.27 grams of water vapor. So under these reaction conditions, I would produce 2.27 grams of water vapor. Just a couple more examples to work. This actually shows you what it looks like. I like this picture a lot. It actually shows you what's happening when you're collecting gas over water. So here we've got hydrochloric acid solution reacting a piece of zinc. And when zinc and hydrochloric acid react, wrong button. It's kind of similar to the reaction we looked at with the aluminum. This would be zinc solid, HCl aqueous. It's a single replacement reaction. It would give me hydrogen gas because the zinc displaces the hydrogen, and zinc chloride. Of course, the reaction is not balanced, but it's not the reaction we're using either. I'm just trying to show you an example of what it would actually look like. So let's see, a 2 here. Zinc is balanced, hydrogen is balanced, chloride is balanced. Okay, it's now balanced. But what's happening is this is generating hydrogen gas, which travels through here, and it's basically displacing water in here. And so what students do this, I've done this at a school I worked at previously, where students did this experiment. And what you do is you fill a graduated cylinder here entirely with water, and then you invert it into the bowl of water below, and it keeps this completely full with water. As the hydrogen gas is being generated, though, traveling through the tube, the hydrogen gas begins displacing the water in the system. And as it displaces it, then this is filled with primarily hydrogen, which you can see here in the picture, primarily hydrogen molecules, but small amounts of water get trapped in there as well. That's what we mean by the gas being collected over water, is a picture like this. So again, this picture is not this example, but I like the picture because it shows you kind of conceptually what it means. Here, how many moles of acetylene are present in a 500 ml sample of gas collected over water at 20 degrees C and a total pressure of 7 to 58 torr? The vapor pressure of water at 20 degrees C is 17.54 millimeters mercury. Well, I know that P total is equal to the pressure of acetylene plus the pressure of the water. So the pressure of acetylene is going to be equal to 750, hold on. Total pressure is 758. So 758 minus that vapor pressure of water. That's in millimeters of mercury. This is in torr. Nice thing about that, you do have to show this conversion, but I know the conversion here. 754 millimeters of mercury is a 1-to-1 relationship. 1 torr to 1 millimeter mercury. So minus 1754 torr. So let's see, 758 minus 17.54 gives me 740 torr. So torr here. So 740 torr. I'm going to need this in atmospheres because I'm going to be using the ideal gas law, and I only know the gas constant with atmospheres. I don't know it with torr. So 740 torr times 1 atmosphere over 760 torr, 760 torr. So it used to be millimeters mercury. Gives me 0.974 atmospheres. Now my ideal gas law, I'm trying to find number of moles. PV equals nRT. So PV over RT. 0.974 atmosphere. 500 mils is 0.5000 liters. R 0.08206 liter atmosphere to mole K. And your temperature is 20 degrees C, which is 20.0, so 293.2 Kelvin to keep your sig figs. 0.974 times 0.5 divided by 0.08206 divided by 293.2, 0.202 moles. Which is going to be this. 2.0203 and 0.0202, slight rounding difference there. I probably rounded somewhere else than the question did in the book, but those are basically the same thing. I know it's not 0.0207 because that's too far off, but 0.0203 would be correct. And one more example in this module. Oh, sorry, I lied. 2 more examples in this module. Okay. When copper metal is added to the nitric acid, the reaction below takes place. Calculate the volume in liters of NO2 gas collected over water at 25 degrees C when 2.01 grams of copper is added to excess nitric acid, and if the total pressure is 760 millimeters of mercury. The vapor pressure of water at 25 degrees C is 23.8 millimeters of mercury. So it's really nice. If it tells me the vapor pressure of water, then I know I'm subtracting it. Otherwise, I have to pay attention to the collected over water, but I have to be given that value somehow. Let's see, 25 degrees C, 201 grams of copper, pressure. I know this is my limiting reactant. I know this is my excess reactant. So that part's nice. I am trying to find the number of grams of NO2 collected. So let's go ahead. I'm trying to find volume of liters. Okay. So let's go ahead and find the number of moles of NO2. I know that it's all dependent upon the copper. I have 2.01 grams of copper. I don't have this example in my notes, so let me actually look up because I don't actually know the mass of copper. Let's see, copper is 63.55. 1 mole of copper, 63.55 grams. And 2 moles of NO2 are produced for every 1 mole of copper consumed. 2.01 divided by 63.55 times 2, 0.063, how many fixed threes? 3 moles of NO2. Now, my pressure here, 726.0 millimeters of mercury minus 23.8 millimeters of mercury gives me 702.2 millimeters of mercury. Convert that to atmospheres. .924 atmosphere. Volume is what I'm trying to find. Number of moles I just calculated. I know my gas constant. My temperature is 25 degrees C, 25.0, so 298.2 Kelvin. I'm going to shrink these down so I have some room. Okay, so I'm trying to find volume. I know again PV equals nRT. Volume is equal to nRT over P. Number of moles, 0.0633 moles. R, 0.08206. Liter atmosphere to mole K. Temperature, 298.2 Kelvin. Pressure, 0.924 atmospheres. Oops, sorry about that. I just dropped the calculator on the tablet. 0.0633 times 0.08206 times 298.2 divided by 0.924. 1.676, so 1.68 liters of NO2 produced. So under these conditions, I would produce 1.68 liters of NO2. And yes, this is the last one. Okay, a gas mixture is made from 1.28 grams of nitrogen gas and 5.37 grams of argon gas. The total pressure of the mixture is 0.975 atmospheres. What is the partial pressure of the nitrogen gas? So I've got 1.28 grams of nitrogen gas, 5.37 grams of argon gas, total pressure being 0.975, and I want partial pressure of nitrogen. I know the partial pressure of N2 is equal to the mole fraction of N2 times the total pressure of the system. So I just need to find the mole fraction of N2. To do that, I need to find the number of moles of each species, 1.28 grams of N2, 1 mole of N2 is 28.02 grams. This gives me 0.0457 moles of N2. Number of moles of argon, 5.37, that is a 5. One mole of argon. And argon weighs 39.95 grams. Gives me 0.134 moles of argon. So the mole fraction of N2, 0.0457 moles of N2. Divided by 0.0457 moles of N2 plus 0.134 moles of argon. The mole fraction here, 0.254. It's pretty hard to read that. So the partial pressure of N2, it's about 25% nitrogen, 0.254 times 0.975 atmosphere. Gives me 0.248 atmosphere. And that's one that's pretty easy for me to check and say, does that make sense in my head? The total pressure is close to 1 atmosphere. The partial pressure is about 25% of it, so 0.248 atmosphere makes sense. Keep working problems with Dalton solve partial pressures. These are really easy examples to convert into or combine with regular gas laws or with manometer calculations, barometer calculations, etc.